All right, welcome to Lecture 5. We went over subatomic particles, protons, neutrons, and electrons and their general charges, and now we're looking at elements and how they're defined by their number of protons. So all atoms on the periodic table are determined by their number of protons. So hydrogen, for example, has 1 proton, so it's on the 1 spot. So if you go across the periodic table, every row, we can see that they're in a numerical order. So the atomic number, also known as Z, is the number of protons inside the nucleus. Keep in mind that while neutrons are important when determining the weight of an atom or how much the atomic mass is, it does not go into play in the number. Looking at helium, for example, helium has 2 protons and it also has 2 neutrons, but we don't look at the neutrons. We only look at the protons when determining the number of stuff here. And remember, electrons do not have weight to them, or they don't have enough mass to really count. So we're not looking at electrons for the number on the periodic table, nor for atomic mass. How they're ordered on the periodic table is you have your atomic number, Z, or the number of protons, and you have your chemical symbol. All of these are chemical symbols, and usually they correspond to the name. So like C for carbon, N for nitrogen, O for oxygen. So going down, talking about isotopes. So isotopes is when the number of neutrons varies. An isotope of helium has 2 protons and 2 neutrons. An isotope of helium would be 1 neutron instead of the normal 2, or 3 or 4 neutrons instead of the normal 2. So an isotope is just when it has more neutrons than it's supposed to, or less neutrons than it's supposed to. Although the number of protons defines the type of an atom, the number of neutrons can vary between atoms of a particular element. This is how we get carbon 14 or carbon 10. The mass number for a particular atom is the number of protons plus neutrons. This describes a single atom. Remember, it's in red. Red means it's important, so make sure you guys are keeping track of this. Isotopes are talked to a lot, and you guys can actually make isotopes, especially in the lab. So here we have an atom that's kind of written this way. So the chemical symbol is X, so this chemical symbol could be C for carbon or O for oxygen. That's just what the X is a standby for. Then the atomic number defines this. Remember, the atomic number is the number of protons, and every atom has a unique number of protons. So if you say the atomic number, you're basically saying the chemical name. And then there's the mass number, or how much it weighs. For a particular type of element, the mass number for the atoms can be different. These are isotopes of each other. Let's take neon, for example. Neon 20, or 20, which is the mass, 10, which is the atomic number, which it means it's neon. Keep in mind, if this was 9 or 11, it would be a different atom altogether, but 10 is neon. So that's why 10 is the same for all of these. However, looks like there's more neutrons per each neon here. So the number of protons, number of neutrons, the corresponding mass number by adding the protons and neutrons together, and the natural abundance percentage. The natural abundance percentage basically means how often does it occur in nature. So if we look at neon 20, it looks like neon 20 is very common in nature. And these aren't all always going to add up to 100%, by the way, because some of these are very radioactive and some of these are man-made, so they're not going to be naturally occurring at all. So now we look at ions, losing and gaining electrons. So when you look at the periodic table, the atoms or elements shown represent neutral, no-charge atoms. This means the number of protons is equal to the electrons. The term for atoms existing in the state is elemental X. X is the atomic symbol. Don't worry too much about trying to remember elemental X and elemental state like that, because I have personally never seen it outside of Gen Chem. So if you're in Gen Chem right now, which this lecture is for, or going through high school or something like that, you can look at it and remember it for exams. But after that, I personally haven't really used it. But if you're going into organic chemistry or inorganic chemistry, even then I haven't seen it in there, but you can still just remember X is like a capital X is like a placeholder. Atoms do not always exist in this elemental state. They never gain or lose protons, as this would change the type of atom. And keep in mind, an atom, as we learned before, cannot change into another atom. That is impossible. It cannot gain or lose protons, but it can gain or lose neutrons becoming an isotope, and it can gain or lose electrons having a different charge on it. Positively charged atoms take sodium, for example. Sodium is relatively neutral-ish. It has a +1 charge, but if you add an electron to it, it would be neutral. So I'm pretty sure this is supposed to be an equal sign, this little square here. So chlorine +1 electron is chlorine minus. So how you would write this is 1 minus or 1 plus. Just imagine there's a 1 in front. It's not +1 or -1. It's 1 plus, 1 minus. Negatively charged atoms or ions are called anions, and positively charged atoms, ions, are called cations. So if you remember, because there's only two things we have to remember here, negatively charged anions, and then positively charged cations. So if you remember negatively anion, the N at the beginnings, these have N's at the beginning, kind of negating that A, but if you know anions or are negatively charged anions, like anti something, then the only other thing we had to remember is cations. So what are cations? Cations are the only other thing it could be, which is positively charged atoms. So if we know that cations are positively charged, like cats are positive, or anions are negatively charged, then we'll know the other one automatically because we only have to remember two things. A little hint, again, to try to figure out a way to remember these, but please come up with your own fancy metaphors and ways to remembering them as well. So for here, we have the same thing as we saw before. The mass number, this is going a bit more in depth. The mass number is the sum of the number of protons and number of neutrons in the nucleus. So that's up here. That's how we determine different number of isotopes. And then the atomic number Z is the number of protons in the nucleus. So N, the number of neutrons, is therefore A minus Z. Because if this is the combination of protons and neutrons, and this is just the protons, protons minus protons leaves you with just N number of neutrons. Now we get into the fun bits of different types of decay. Alpha decay is defined as the loss of a helium nucleus, 2 protons and 2 neutrons. So the parent nuclide, or that's just another word for nucleus, or the center of an atom, with where the protons and neutrons are. So the parent nuclide with 23892, and this is the daughter nuclide, or basically what comes after this. By the way, all these types of decay, alpha, beta, gamma, like these are very, very kind of like deadly for you. Do not mess with any type of like radiation or decay, guys. To remove a helium atom, so 2 neutrons and 2 protons, we can turn this U into a TH. So this is the way to turn it into another atom. All right. So these decay is giving it new charges and turning an atom into a different atom. I know I said that's impossible. However, it's like the same atom. However, it's like taking things out of its nucleus to create a helium. So decay is very interesting, and I'd highly suggest you guys do your own research about it, because they can explain it a lot better than this. The most important rule is an atom cannot change into another atom, except for in this case of decay. Definitely suggest looking up decay. It's very interesting. So beta decay is defined as the loss of an electron from an atom. However, this electron is not one of the normal electrons in the atom. The daughter nuclide does not have a charge. Rather, the emitted electron comes from the breakdown of a neutron. This is a kind of confusing to look at. Just know that 1 neutron goes to 1 proton and 1 electron. So for example, if we take radium, I'm not sure what AC is, but radium goes from 228, 89, and it goes to 228 over 89. So over 89, this is the number of protons plus 1 electron. So what you can write here is this plus 1 electron. You don't have to put 0 over -1. I've never had to do this. You can write 1 proton, technically a 0 for a neutron, but 1, and -1 electrons, or e to the minus. If you put e to the minus, that's also another symbol for an electron. So beta decay results in an atom having the same mass number, the top part here, so the same number of neutrons and protons as a parent atom, and having 1 additional proton. So a fun hack here is you look at the bottom. So this is also why he divided it like this. Oh, he couldn't figure out how to get rid of the lines. The reason why it's kind of like separate out of this is if you add 89 and -1, you get 88. So this is also a way you can figure this out. Gamma decay is a completely separate symbol. So this is the symbol for gamma. It goes down, there's a loop, and then it goes back up. It's defined as the release of a high energy photon or a light particle. So a light particle is not the same as an electron in this current context situation. Gamma decay results in an atom having the same mass and atomic numbers as the original atom, but it's plus a gamma. Here, it's a type of radiation, kind of like the Hulk when he messed with gamma rays. This is also kind of the same thing. This gamma radiation, gamma decay really messes you up. So for this example, 238 over 92, 234 over 90. So we got that helium atom, but we also have the gamma here. So this is basically saying you could kind of combine it with different types of radiation. So next we have atomic mass. So the average mass of an element's atoms. So chlorine, for example, has 35.45 atomic mass weight, or grams per mole. So why is this not a whole number? It's because this chlorine actually occurs in has two naturally occurring isotopes. So this is kind of like the combination of it. This is how we find out the grams per mole. So we have chlorine 35 and chlorine 37. Chlorine 35, as we can see, its natural abundance percentage is a lot higher, so we know that it occurs a lot more in nature. So we take 35 AMU, or atomic mass units, because 35 here, over 1 times its percentage over 100%, because it's percent out of 100% total, plus 37 with its percentage. What do we get? Well, if we go all the way along the top, if we divide these two percentages and go all the way over, we get 35.48 AMU. Where do these come from to start with? Because now we know our atomic mass, but how did we even figure out these naturally occurring percentages in general? Actually, it is from mass spectroscopy. So mass spectroscopy, or mass spec, is measuring the mass of atoms and molecules. So as we can see here, a sample goes through and a heater vaporizes a sample, and the electron beam ionizes the sample, and it gets accelerated, goes through some magnets, and then, as we saw before, kind of like with Rutherford's gold foil experiment and the other experiment, it gets separated, and the lightest ions, the left side of the detector, and the heaviest hit the right side. So basically it separates ions based on how much they weigh. So then it'll pop out a graph kind of like this. This is the very, very nice graph. So if you look at actual mass spec data, it's not going to be as clean as this at all. But the height of peak on the y-axis indicates the relative abundance of the isotopes. That's how we know. This is our 75.77%. This is an estimation kind of out of 100. The scale is definitely off over here a little bit. And we can see that chlorine 37 is a little bit lower. So now we can use this mass spec data to determine the abundance of the isotopes. If you're given this Ag, or silver mass spectrum, you can calculate the abundance because you got the intensity of isotope of interest, so 100%. It's what we got here, 107, and plus 92.9, which I'm pretty sure they got from this yellow. Okay, so we're given the intensities here, okay. So here for silver, when we get the mass spectrum popped out, it will give us our intensities, and we can put the combined total of the intensities on the bottom. And for 107, we have the given 100%, so it's given over our total added together, and it's our given right here, 109.92.9 over our total. And then we multiply by 100 and we get this. So what is the atomic mass of silver, assuming the isotopes have the exact mass as shown here? I am going to let you guys kind of figure that out. Remember, using what we know before from here. So I want you guys to try yourself to determine the AMU, or atomic mass, of silver based on your two isotopes that you have here. So next is atoms in the mole. How many particles? So because atoms and molecules are so tiny, we don't deal with them on the individual level, rather we deal with huge numbers of them. Like for example, a drop of water contains roughly E21, or 1 times 10 to the 21 water molecules. Because we deal with very large numbers of atoms or molecules, chemists have come up with a special unit, because again, we are lazy, and we've come up with the mole. So yeah, I know you've heard this before in the previous lectures. 1 mole is 6.022 E23 particles. This is also known as Avogadro's number. It's derived from the number of C12, or carbon 12, isotope, atoms in exactly 10 grams of C12. So the number of carbon 12 atoms in exactly 12 grams is 6.022 E3. So the mole is often shortened to MOL because, again, chemists are lazy. And then for molar mass, what is the mass of 1 mole of a substance expressed in grams? So what is the molar mass of water? Well, we take H2, so 2 hydrogens, so 1.0008 times 2, and 1 oxygen, H2O, 16, and we add them all up together, and then you'll have 1 mole, or 6.022 times 10 to the 23, of water molecules. Converting between mass and amount number of moles, so if we have our molar mass that we got, 18.016 grams, we can use this to convert it into particles. So we could either go 1 mole over grams or grams over moles, depending on what we need to convert between the amount of number of moles. If you have, these are example problems for you guys, using these two. If you have 63.056 grams of water, how many moles of water do you have? So keep in mind, if we want to find moles from grams, we have to use this in order to cancel out the grams. So I'd start with, just to help you out on this one, 63.056 grams over 1 times 1 mole over 18.016 grams of water. The grams of water will cancel out because they're across from each other. And then you're going to multiply on the top, multiply on the bottom, and then divide your top and bottom, and that'll give you your answer. So go ahead and try this out. We got some cute little moles here. We can also use the 6.02 E23 to convert between the number of individual atoms and molecules and the atoms or molecules and moles of atoms or molecules. If you have 1.3 moles of nitrogen, how many molecules of nitrogen would you have? So remember, multiplying on the top, multiplying the bottom, dividing top and bottom, you'll get this many molecules for this many moles of nitrogen gas. Nitrogen gas, I know it is because it's N2. Always necessarily be a gas, but usually if it's like N2 or like O2, they're stabilizing each other, it usually means it's a gas. So if you have this amount of molecules, how many moles do you have? It's easy. You just kind of go backwards here. I'd suggest you try it out. Using Avogadro's number and molar mass together, so this is longer. You're going to have 3 separate equations here, and you're going to multiply all 3 on the top and all 3 on the bottom. Could be more for either of these, could be less. You guys are going to have to figure it out and try it out. I believe in you guys. And going through here, it helps you out a little bit. This is the end of this lecture, so make sure you guys go ahead and go back through and practice all of these. And if you want more practice, I would highly recommend looking up other videos, looking online, going through your textbook, asking professors, classmates, teachers, and just go through and make sure that you have a good understanding of this, because not only will this help you with conversions in general, like from the first lectures, but it's going to be really, really, really helpful because I'm in my late senior year of my biochemistry bachelor's degree right now, and I use this quite a bit, especially conversions between atoms and moles, because I need to know the moles of something, I need to know the grams of something. Usually I need to know the grams or convert between grams over moles to something in order to make dilutions, in order to make stock solutions. So I do use this quite often, and almost every subject in chemistry is going to use these quite a bit. Keep in mind that it is very, very important that you guys get confident on conversions now, so that way you will be prepared for the future, because I honestly wish that I paid way more attention to general chemistry. Please make sure you guys study and look at multiple different sources. I shouldn't be your only source. Your textbook shouldn't be your only source of information. Make sure you're looking at multiple different sources, and please ask questions. All right, thank you so much. I will see you in lecture 6.